Okay, well, I guess I'll introduce you since you're my student. This is Reed Petersen's master's thesis defense. He's done some really nice work with silicon carbide. Kind of taking off for us right now. There's a lot he's not going to show you today. That's a good thing, though. But we practice this talk, and it's a really nice talk, very clear, very clean. Go ahead, Reed.
Cool. Thanks, Dr. Hubby, for the warm introduction. Thanks, everybody, for coming. As he said, my name is Reed Petersen, and I'm now working on completing my master's in physics for those of us who haven't met. So this presentation is an overview of my research regarding silicon carbide nanocrystals. I'll talk about some of the problems in the area and my attempts at clarifying them. Also, I'm recording this presentation on my end, just so you know. And if you have any questions, you can feel free to ask them anytime during the presentation, and I think there will be lots of time after the presentation to ask questions as well. I'm going to present our current research on silicon carbide nanocrystal synthesis and their properties. And I'm going to try to explain as much of the applicable physics as possible without getting bogged down into the material science or chemistry aspects of the research, though they are important, so I will touch on them briefly. Here's an outline of what I'll be covering in this presentation. I'll first give a background and introduction to silicon carbide materials with specific emphasis on silicon carbide nanocrystals. I'll discuss the most common synthesis approaches for silicon carbide nanocrystals, and then introduce the technique that has been developed here at NDSU. I will cover details and reasoning for choosing the precursor we used, and I will briefly describe our non-thermal reactor setup, as well as the methods used in the setup. Following that, I'll discuss the results and the conclusions drawn from the results. So starting out, I want to describe silicon carbide to you. Silicon carbide, abbreviated as SiC, is an extremely hard semiconducting material containing the elements of silicon and carbon in a 1-to-1 ratio. Because silicon carbide can rarely be found in nature, it's typically made synthetically. Silicon carbide is chemically inert, and it does not oxidize until exposed to high temperatures. And silicon carbide does not melt at any known temperature. Instead, it directly sublimes when heated. Silicon carbide is commonly mass-produced for its impressive mechanical properties. It's used in many mechanical applications because of its extreme hardness. Silicon carbide is actively used for abrasives and bulletproof plates, and fibers of silicon carbide can be added to a polymer to form matrices with a really high strength-to-weight ratio. To give you an idea of just how hard silicon carbide is, the beta polymorph, which is the type created in our lab, is about 95% of the hardness of diamond. A polymorph is a varied crystallographic structure. So there exists over 250 different polymorphs of silicon carbide. So it can exist in cubic form, hexagonal form, and many more different types. Because of its impressive mechanical properties, silicon carbide became a popular material in the 19th century and was the subject of many scientific experiments at that time. One experiment in particular in 1907 was Henry Joseph Round's experiment, in which he made the first LED by applying a voltage across a silicon carbide crystal. This discovery of the LED phenomena paved the way for large-scale production of green and blue LEDs. And silicon carbide was used as one of the few ways to make short wavelength LEDs up until about 1986. In that year, researchers Akasaki, Amano, and Nakamura discovered gallium nitride as a material for bright blue LEDs. And as some of you may be familiar with, in 2014, the Physics Nobel Prize was awarded to them for that discovery. So the images here are commercialized products of silicon carbide. The left-hand picture displays a large silicon carbide single crystal, which was manufactured by Texas Instruments, which in the manufacturing process would eventually be sliced into wafers and etched for functionality. The right-hand picture is commercially available silicon carbide powder grit, which is used to polish stones. So all of this to say, silicon carbide doesn't have applications that are out of reach. It's used today, and it's only finding more applications as research advances and technology has more demanding requirements. I want to give a very brief background of nanoparticles and some of their important properties. Nanoparticle research refers to a field that includes synthesis and development of particles ranging in size from 1 to 100 nanometers. Nanoparticles have properties that lie between the bulk materials and individual molecules. Nanoparticles are unique from bulk materials because of their greatly increased surface area and small volume. Likewise, nanoparticles are unique from individual molecules because they can form lattices and have group effects, such as semiconducting properties. Most often, nanoparticles are defined as having an inorganic core. Carbon is an organic element when bound to hydrogen, but carbon compounds such as carbides are classified as inorganic. Inorganic nanoparticle cores are often arranged in lattice structures. More specifically, this makes them nanocrystals, which are a subset of nanoparticles. And in this study, we will be investigating specifically nanocrystals. Sometimes the dimensional confinement of nanoparticles is small enough to confine the electron wave function of the material. And when materials become small enough to meet this condition, their electronic properties deviate significantly from bulk properties. And this is what's called quantum confinement. As nanoparticles have such a large surface area when compared to a similar mass of bulk material, the surface has a big effect on the behavior of the material. To passivate surface effects and defects, a core shell structure is often adopted. Colloidal core shell nanoparticles contain at least two semiconducting materials in an onion-like structure. In core shell nanocrystals, the shell provides a physical barrier between the core and the surrounding medium, and this protects the core, making the nanoparticles less sensitive to environmental changes, to surface chemistry, and photooxidation. Not all synthesis techniques for semiconducting nanoparticles will work for silicon carbide due to silicon carbide's high stability and tough mechanical properties. Some techniques used for silicon carbide synthesis can be broken down into two subcategories: the top-down and the bottom-up approaches. The top-down approach begins with the bulk material, and it reduces it down to nanoparticles from there. One prominent top-down synthesis route is through carbothermic reduction of silicon, in which a carbon source and a silicon source are placed near to one another and heated for over 6 hours to several hundred degrees Celsius under an inert atmosphere. After some lengthy post-processing to remove unwanted and unreacted precursors, the resultant is commonly beta-type silicon carbide nanocrystal powder. Most of this powder is sintered or heavily aggregated when it's made, which is a major disadvantage of this technique. One form of commonly used silicon carbide nanoparticle is in the form of one-dimensional whiskers. Silicon carbide whiskers are a single crystal fiber with a diameter in the nanoscale and are used to enhance the tensile strength and heat stability of composites. They are made by carbothermal reduction of silica at 1400 degrees Celsius typically. Another top-down approach is based on electrochemical etching of bulk silicon carbide. In this technique, a wafer of silicon carbide is placed in a reservoir of the etchant, which is usually hydrofluoric acid with another solvent such as ethanol, and that's under a current flow. This creates a porous silicon carbide matrix in the wafer through which the individual nanocrystals can be liberated by sonication in a bath. This method is nice because the end product is predictable, because the structure of the silicon carbide nanocrystals will always take the same form as the parent wafer. So if you start with a hexagonal parent wafer, then you'll end up with hexagonally formed silicon carbide nanocrystals. Notably, however, a top-down nanoparticle synthesis technique route that's missing for silicon carbide is grinding. Because silicon carbide is so hard, it will quickly dull any blade that's made out of anything that is not diamond, making grinding techniques unfavorable for silicon carbide, especially as a commercial approach. The bottom-up approach begins with the molecular precursors, and it builds the nanoparticle through nucleation or growth, and can be performed through several routes. The bottom-up approach is typically favored for its efficiency and its high-quality product. A common bottom-up approach for the synthesis of silicon carbide nanocrystals is the sol gel technique, which works for many of the group 4 semiconducting nanocrystals. So it also works for germanium and silicon. This technique can be summarized by two main steps. First, a gel is made using a polymeric carbon and silicon source, and this gel is heated to over 1000 degrees Celsius, and a carbothermal reaction takes place. This bottom-up approach is generally very high yield and produces dispersive particles. However, it is limited when compared to the other methods by the problem of mutual salting out of the two precursors, which must be chosen carefully for the process to be successful. Unfortunately, perhaps the biggest synthesis technique that's missing from silicon carbide research, which many other semiconducting nanoparticles have as an option, is liquid phase colloidal synthesis. It's not feasible for silicon carbide because the precursors would have to be very unstable and highly exothermic to be able to form silicon carbide, which is very stable. Thus, alternative synthesis techniques must be explored for silicon carbide. There are also plasma techniques for bottom-up synthesis of silicon carbide, which will be detailed in the next slides, as these are the techniques employed in this thesis. Notably, all bottom-up non-plasma synthesis techniques of silicon carbide, whether bulk or nano-sized, require exposure to high temperature. And the top-down approaches that I just mentioned all require bulk silicon carbide, which is made through high temperature techniques. This high temperature is typically in a furnace or an air-free chamber. High temperature ovens are costly, and many purification steps have to be performed to obtain a relatively pure nanocrystalline product in the end. Plasma synthesis solves these problems because the resultant nanocrystals are of pure form and the heat is localized to a smaller location. In non-thermal plasmas, which is the type we use, the heat is localized to the nanocrystal surfaces themselves, which creates a lot less waste heat, making it a more efficient process. Before detailing our plasma synthesis technique, I want to describe the plasma techniques of some other groups. And I'll start with the thermal plasmas. One thermal plasma technique is laser pyrolysis, in which gaseous precursors, usually silane and acetylene, absorb laser radiation, which directly dissociates the precursor molecules, and a nucleation and growth chemical process proceeds within a flame. The flame has a temperature of above 1200 degrees Celsius, and the species in the plasma are all at a similar temperature, making it a thermal plasma. The self-propagating flame technique is similar to the laser pyrolysis technique, except it doesn't use a laser, and instead the flame propagates through an exothermic reaction. Another thermal plasma synthesis technique that's been used for silicon carbide is the plasma expansion process. The experimental configuration of that process consists of a DC plasma torch into which the precursors are fed, followed by a chamber for nanoparticle collection. Generally, the DC plasma source requires a very high power to sustain the plasma. Some sources cite that it requires 100 or more amps and 20 or more volts to sustain the plasma, as the only plasma coupling is through the direct breakdown of the media, in a similar method to welding. So there's an arc that's struck, and the nanocrystal reaction takes place in that arc. While not all DC plasmas are thermal, the plasma in the expansion synthesis process is thermal because of the morphological requirements of the reactor. Finally, the technique used in this thesis is the non-thermal plasma process. This has been performed before by several research groups to achieve hollow crystalline silicon carbide nanocrystals in low pressure plasmas, amorphous silicon carbide nanoparticles in low pressure plasmas, and both amorphous and crystalline silicon carbide nanoparticles in atmospheric pressure non-thermal plasmas. But silicon carbide nanocrystals have never been made directly in a low pressure non-thermal plasma, which is the motivation for this thesis. So I want to cover some non-thermal plasma basics. The non-thermal plasma derives its name from the fact that the electron temperature is much hotter than the temperature of the larger species in the plasma, such as the silicon, carbon, or argon neutrals and ions, as only the electrons are the hot species. Their velocity is much faster than the larger species, and they have a hard time distributing their energy to their larger species counterparts. An example of a common non-thermal plasma is found within a fluorescent lamp, in which a mercury vapor gas is ionized. And those are just common fluorescent lamps that we interact with daily. The electron temperatures in those lamps reach 1 to 2 electron volts, which is up to 20,000 degrees Celsius, while the rest of the gas remains slightly above room temperature, making it a safe household device, besides the mercury. Non-thermal plasmas are efficient because there's little waste heat. When compared to nanoparticle synthesis by thermal DC plasmas, non-thermal AC plasmas, in our case we use radio frequency plasmas, can be several orders of magnitude lower power. Our NDSU reactor has made crystalline nanoparticles from as little as 12 watts of net power put into the plasma. At such low powers, the reactor does not even require active cooling to remain operable. This efficiency is even more advantageous for making silicon carbide because it is a high melting point material. Silicon carbide can be made directly in crystalline form in the non-thermal plasma, since the nanoparticles are heated by surface reactions. And those surface reactions come about because of the electron collisions. So in this figure, on slide 7, you can see some elementary processes in the plasma. So pictured here is the ionization of a neutral atom. So an electron with high velocity strikes a neutral atom, knocks off another electron, so that atom becomes ionized. Over here, you can see the re-emission of an electron. So a high velocity electron comes in, but instead of another electron being kicked off, there's instead a photon, and that's why the plasma glows. There also exists an electron sheath around the plasma, which charges the large surfaces in contact with the plasma, and it charges them negatively with electrons. Things like the reactor walls and the nanocrystals are negatively charged. We chose a low pressure plasma for the NDSU reactor, but this thesis investigates the low end of intermediary pressure plasmas as well, with pressures in the tens of torr. Our NDSU reactor is optimized for use with liquid precursors. So the precursor chosen was a liquid. An ideal precursor would have low toxicity to humans and would be non-pyrophoric. And the organosilicon compound tetramethylsilane fits these requirements well. I'll refer to tetramethylsilane interchangeably with its abbreviation TMS. Interestingly, this process transforms an organic precursor, the TMS, into an inorganic material, silicon carbide. Tetramethylsilane is nonpolar and has a very low vapor pressure. It has a boiling point of only 26 degrees Celsius. So if you get just above room temperature, it starts to boil. This slide details the structure of TMS, which is tetrahedral at both carbon and silicon. The left-hand image is a structural formula, and the right-hand image is a 3D ball and stick model of TMS. TMS is commonly used in nuclear magnetic resonance spectroscopy, abbreviated as NMR, as a standard for calibration due to the high symmetry of the compound. All 12 hydrogen atoms in TMS are equivalent, so its proton spectrum is a very sharp singlet. It is also used as a solvent in NMR spectroscopy because of its low boiling point. So over time, when the measurement is finished, the original sample can be recovered just by letting the TMS evaporate out of it. These two properties of TMS drive a consistent demand in the market, which drives down the cost and makes it easily available to purchase online. And this is one of TMS's biggest advantages. It's in high production in the market today and is readily available. Most other organosilicates are only available via special order from suppliers in small batches, if available at all. TMS has been used to make silicon carbide nanoparticles and thin films in prior research. It's a fairly well-used precursor, which is another reason we're using it here. As TMS has a carbon to silicon ratio of 4:1 in molecular form, that is, for every 4 carbons, there's 1 silicon atom, prior literature reports indicate an excess of carbon in the final formed nanomaterial. In 2008, Lin and others came out with a paper that reported detuning the carbon content of silicon carbide nanoparticles made from TMS by adding hydrogen into the flow of their plasma. They found that hydrogen preferentially consumes the carbon content of the precursor while leaving the silicon ions to incorporate into the nanoparticles. And this even works in the silicon-rich case to decrease the carbon content past that 1:1 carbon to silicon ratio. This figure is a ternary plot of the possible combinations of composition ratios between silicon, carbon, and hydrogen in the plasma. The blue line marks the only parameters that can be reached using TMS and hydrogen in our plasma. So that's why it's called the TMS and hydrogen constraint. And if you read the chart, you'll find that the blue line represents a constant 4:1 ratio of carbon to silicon, and it varies the amount of hydrogen. That 4:1 carbon to silicon ratio is again due to the precursor TMS. And this ternary plot represents the ratio of total atoms in the plasma. So it's just kind of a parameter space that you can get your mind around. This image is the plasma reactor setup at NDSU, and it's gone through many iterations. The original apparatus was made by Todd Pringle and was used to create silicon nanocrystals, and it has since been adapted and expanded to make the silicon carbide nanocrystals described here. So the basic working principle of the reactor is that a precursor gas is fed into a bubbler, or an organometallic bubbler, where the precursor sits. So that's where the TMS is. And as the precursor gas flows through it, it carries the precursor downstream, meets with a couple other gases, which I'll talk about in a moment, carries them into the reactor where the nanocrystals are made, and down into a mesh where the nanocrystals are collected. The precursor gas we used is a mixture of 95% argon and 5% hydrogen. An example of a liquid bubbler can be seen in this figure. The bubbler contains the liquid precursor in the bottom, into which the input gas bubbles. So bubble starts at the bottom of the liquid, and as it rises, molecules of the liquid precursor enter the gaseous bubble, which vaporizes the precursor. The constant flow of gas into the bubbler pushes precursor vapors downstream and into the plasma reactor. The bubbler was cooled in an ice bath down to near 0 degrees Celsius during runs to further reduce the vapor pressure of TMS, allowing for more control of the precursor flow rate. The flow rate of the precursor in a bubbler follows this equation, where Q precursor is the precursor flow, so just the atoms of TMS flowing, and that's measured in skim, so that's standard cubic centimeters per minute. Q gas is the flow of the precursor gas itself, that's flowing into the bubbler. P precursor VP is the vapor pressure of the precursor. We measured it in torr, and P bubbler is the pressure of the headspace of the bubbler. So what you can get from this equation is that as you increase the bubbler pressure, the precursor flow will decrease. But because the vapor pressure of the precursor is so high, the bubbler pressure has to remain high to keep the precursor flow rates in a controllable zone. If the precursor gas is introduced into the reactor at too high of quantities, it will take energy from the plasma and the particles won't crystallize. They'll instead remain amorphous, which wasn't what we were looking for in our case. So once the precursor gas leaves the bubbler, it joins up with a carrier gas. The carrier gas enables an operator to control the plasma characteristics without requiring the full flow of gas to be directed through the liquid precursor. In our system, we use the same mixture of gas for carrier gas as for the precursor gas. Another gas used in the system is the reaction gas, which mediates the precursor in the plasma. In the system, and as was alluded to before, hydrogen is used as a reaction gas to control the amount of excess carbon in the final formed nanocrystals. So the vapor saturated precursor gas, the carrier gas, and the reaction gas all meet upstream of the reactor and are introduced into the plasma mixed together. The reactor tube itself can be adjusted based on the desired traits of the plasma, which generally follows Bernoulli's equation for flow through a pipe. So in this equation, P is the pressure of the fluid, rho is the density of the fluid, V the velocity of the fluid flowing through the pipe, G is the gravitational constant, and H is the height of the fluid. And subscripts 1 and 2 denote the various system configurations that can exist. For this system, we can neglect the third term on either side of the equation because the density of the gas is assumed to be small. As well, the gravitational constant is small and the height change in our system is very small. So this third term ends up being negligible. So this shows that for a larger diameter reactor tube, the gas flows slower through the pipe. Generally, to make homogeneous powders in this system and reduce reactor wall deposition, a larger diameter glass reactor was chosen. This reactor measured 0.69 inches in inner diameter and 1 inch in outer diameter, making the wall about 0.16 inches thick. That's a really thick wall. Such a thick wall allows for high plasma power to be used, which is important. The factor with the largest effect on nanocrystal sizes is the residence time. The residence time is defined as the amount of time that gas flows through the plasma, and it's inversely proportional to the velocity of the gas, which is shown in this equation. Just from elementary physics, V velocity is equal to distance divided by time. So time is inversely proportional to velocity. So this is the equation for velocity flowing through the reactor, which gives V in terms of QTP, which is the flow of the gas adjusted for temperature and pressure. And to adjust for the non-standard pressure, you have to add this term right here to this equation to get it in terms of standard temperature and pressure, where QSTP is the flow read by the mass flow controller. PSTP is equivalent to about 760 torr, because that's just the pressure at standard pressure. And P is the pressure measured by the pressure transducers in our system. A is the cross-sectional area of the reactor. And the final part of this equation implies that this is a non-thermal plasma, or that the temperature that we're operating at is equal to standard temperature and pressure, which is room temperature. So using the velocity found in this equation, the Reynolds number can be computed. And for the 0.69 inch inner diameter tube, the flow ends up being transitional between laminar and turbulent flow in the reactor. Connecting to the reactor, about 3 feet of 5 millimeter inner diameter tubing was used to deliver input gases to the reactor. This resulted in turbulent flow, again from the Reynolds number, which mixed the gas phase molecules upon entrance into the reactor and minimized phase-rich pockets, and also engendered a uniform resultant powder. On the output of the reactor, a fine stainless steel mesh was used to collect nanoparticles. As the nanoparticles are carried along in the gas, they strike the mesh and they stick onto it. So the pressure in the reactor was moderated manually using a gate valve and was kept constant for the run, for every run, and it was always kept between 5 and 40 torr. During a synthesis reaction, which was typically an hour in length, a considerable amount of deposition forms on the reactor walls. Most of the deposition in the synthesis process happens right around the electrode locations, but some also happens downstream. where the powder can be seen collecting lightly on the walls of the reactor, as in this image. The nanocrystal powder collects on the walls downstream of the plasma because there's no opposing force to stop it from doing so. The particles bump into the wall, and no plasma sheath exists to repel the charged nanoparticles. So in this image, you can see the length of the plasma, and where that plasma ends, you can see in this image, is where the nanoparticle deposition begins. And that is, again, because, as I mentioned before, the nanoparticles are negatively charged, and anything in contact with the plasma is negatively charged, so they'll repel each other and they won't collect there. But downstream of the plasma, that's not necessarily true. And the particles deposited downstream of the reactor represent one of the largest yield losses in the system. And it's largely unavoidable without a major overhaul to the system. So the characterizations performed on the powder were X-ray diffraction, abbreviated as XRD, thermogravimetric analysis, abbreviated as TGA, transmission electron microscopy, abbreviated as TEM, and optical absorption measurements. As well, we measured the solubility and the yield of the powder. The system can be tuned in many different parameters. For the studies presented in this thesis, the tuning parameters chosen to vary were the reactor pressure, the reaction gas flow rates, and the carrier gas flow rate. As can be inferred from the velocity, that velocity equation that I showed earlier, an increase in flow of the gas through the reactor will result in an increase of velocity through the reactor. They're linearly dependent with each other. And an increase in flow of the reactor will result in an increase in velocity through the reactor. So therefore, a decrease in the pressure of the plasma, all else being equal, will also increase the gas velocity through the plasma. And the faster the gas moves through the plasma, the shorter the residence time. Thus, these tuning parameters should allow for size tuning of the nanoparticles. The reaction gas, the hydrogen that we add, allows for tuning the carbon content of the nanocrystals, which tend to be either carbon-rich or silicon-rich. So this figure on slide 16 displays some of the first powders made in the reactor. And you can see there are some flakes in some of the powders that were created. The flakes were the result of doing multiple runs in the same reactor without cleaning it. And these flakes were avoided in the characterization of the powder as they weren't consistent. The runs that composed the flakes would be difficult to reproduce in a meaningful way. But despite this fact, the flakes could be potentially attractive as a future study because they exhibited some photoluminescence, whereas the rest of the powders did not exhibit photoluminescence. The dark powdered samples, this figure, indicate an excess of carbon in the powder, while the lighter / yellow colored powders indicate an excess of silicon in the powder. This suggests that it has a similar absorption spectrum to silicon because silicon is also yellow, and we saw that when we actually took the absorption spectra. And this wide variation in color demonstrates the change in optical and electronic properties of the material, and that's mostly based on surface composition. The yield of the powder was on par with other non-thermal plasma synthesis systems, which was on the milligram order of magnitude. A typical 1-hour run would allow for the collection of between 6 and 10 milligrams of powder, but would depend on how much hydrogen was used because the hydrogen consumes part of the precursor. The powder collects on the mesh wires, so its collection varies linearly with cross-sectional area covered by the mesh. So because the nanocrystals collect on the mesh first and deposit upstream from there, the gas flows between the nanoparticles, and the powder remains in a porous open fractal geometry. Directly out of the synthesis system, the powder is expanded about 10 times from wetted aggregated packed spheres. And to see it visually, a small amount of solvent was added to a sampling of powder, as pictured here. The powder goes into solution and dries in a much more densely packed form as the solvent evaporates. So this image shows 1 milligram of powder, which was wetted with about 10 microliters of alcohol solvent. As was alluded to before, the surface of the silicon carbide nanocrystals can either be silicon or carbon-rich, and that's usually in the form of amorphous silicon or carbon. The solubility of the nanocrystals in alcohols strongly depends on how much excess amorphous carbon or excess silicon is present in the sample. Research on amorphous carbon coatings is significant, and there's even some commercial products available that utilize the technology, such as scratch-resistant thin films. Carbon as a shell has potentially useful properties due to the many bond hybridizations available to the carbon material system. Despite its potential for functionalization, excess amorphous carbon on the surface has the potentially negative impact of decreasing the solubility of the silicon carbide nanocrystals in alcohol solvents. To separate the particles from each other, the solutions were sonicated for 4 hours, and the particles that stayed in solution after being left overnight, or for about 8 hours, stayed in solution indefinitely afterwards. The nanoparticles generally went into solution in ethanol, which was described in other papers, as the silicon carbide nanoparticles have intrinsic solubility in ethanol due to their charge. The samples with large amounts of excess carbon would collect at the bottom of the vial if left to sit for adequate time. The particles did not dissolve in water without some processing, but they do in alcohols, indicating that the particles required a medium polarity solvent, or a relative polarity between 0.5 and 0.8. Indeed, they also dissolve in methanol and isopropanol. So this image demonstrates the increased solubility of silicon carbide nanoparticles when the excess carbon is removed. The left vial contains a sample of unprocessed silicon carbide nanocrystals sonicated in isopropyl alcohol for 4 hours. The right vial contains a sample of nanocrystals after removing the excess carbon and then sonicating in isopropyl alcohol for 4 hours. So this photograph was taken after the two solutions had been left sedentary for several hours, and it's clear to see that the sample with excess carbon has aggregated and settled to the bottom of the vial, while the sample without as much excess carbon stayed in a uniform solution in isopropyl alcohol. So now the question is, how do you remove excess carbon from the nanocrystal while leaving the underlying core the same? To remove the excess surface carbon, several methods could be employed. The two most common methods are acid-based removal and thermal oxidation. The acid-based removal route requires the use of concentrated nitric acid, which is a dangerous oxidizer if you're familiar with it. Due to this, thermally oxidizing the carbon away was our preferred method. We used a thermogravimetric analyzer, or TGA for short, to controllably oxidize the carbon at a constant temperature. Using the TGA also gives a quantitative measurement for how much carbon was removed from the powder. One sample, which had about 6% excess carbon, is pictured here, was kept in the TGA for 5 hours at 500 degrees Celsius to bake off the carbon. The data from the oxidation process is displayed here. To read this chart, the temperature ramp is on the primary y-axis, and that's the data that's colored black. And so it's just a constant ramp at 10 degrees Celsius per minute up to 500 degrees, and then it's held steady. On the secondary y-axis is the mass of the sample, which you can see decreases steadily over time. And on the x-axis is time. So the sample started at about 0.65 milligrams, and it ended at just over 0.61 milligrams, meaning that the sample has approximately 6% excess carbon by mass. This image displays a transmission electron microscope image of a sample of silicon carbide nanocrystals with some of the most excess carbon on the surface of any samples we measured. The amorphous shell can be seen around the lattice planes of some of the particles and is up to 1 nanometer thick. And this is in the most extreme of cases. As the natural ratio of carbon tends toward the 4:1 ratio due to the precursor, carbon excesses can be very high without the addition of hydrogen. The individual particles can be viewed with an electron microscope, and the size and morphology can be directly seen. TEM allows us to peer at individual particles to identify their size, composition, and shape directly. So the particles that we made were spherical and formed in sizes between 1.5 and 4.5 nanometers in diameter typically, depending on the reactor conditions. The main parameter of the synthesis system used to vary size was the carrier gas flow rate and the reactor pressure, because they were the least intertwined variables. The smallest particles were achieved with high flow rates. These two images display some typical TEM images taken of the particles. From the zoomed in view on the right, the individual lattice planes of the particles can be seen. So you can see some going this way, some going that direction as well. So the left image is a bird's eye view of the particles, the right, the zoomed in image, and these particles were directly harvested from the mesh. So we just scooped them off of the mesh that we collected. From TEM images, we can measure both the particle size by measuring the diameter of the particles directly, and the lattice spacing of the particles to confirm that the powder is indeed silicon carbide and to determine which polymorph of silicon carbide we have. TEM analysis of our samples has consistently revealed lattice spacings close to 0.25 nanometers, which can be indexed to the 111 plane of beta silicon carbide with a cubic unit cell parameter of 0.436 nanometers. This observation is consistent with universal experimental findings that the cubic crystal structure, or the beta structure, of silicon carbide is more probable than the hexagonal structure for small nanocrystals, that is for nanocrystals below about 5 nanometers. So this image, it gives insight into our TEM analysis technique. The yellow ring around a nanoparticle displays the size measurement, and the inset graph shows the gray intensity of a line drawn through the nanocrystal perpendicularly to the lattice planes and averaged across 20 pixels. A brief calculation of the example in this figure shows that the average lattice spacing for the nanocrystal is equal to the size of the nanocrystal, or the diameter, which was 3.5 nanometers, divided by 14, which is the number of lattice planes that can be counted just by counting the peaks of those lines. That comes out to 14. So 3.5 divided by 14 gives us 0.25 nanometers, which is the expected dominant 111 lattice spacing for beta silicon carbide. And that's one piece of the evidence that leads us to believe that this is, again, the cubic form of silicon carbide. Further confirmation of the beta structure of the powder is found using XRD. And XRD can also be used to find the size of the particles through the Schrödinger equation, which is displayed here. In this equation, tau is the mean size of the ordered domains. K is the shape factor, which was taken to be 0.94 for spherical crystals with cubic symmetry. Lambda is the X-ray wavelength. Beta is the line broadening at the half maximum intensity, and theta is the Bragg angle. Due to the Schrödinger-derived sizes being dependent upon the crystal size, it's helpful to keep in mind that the actual size of the particles may be larger depending on how much amorphous material coats the outside of the nanocrystals. This data displays the XRD data taken for Schrödinger-derived sizes of 4.12 nanometers, 3.46 nanometers, and 2.87 nanometer particles, all showing strong line broadening. The 111 peak is the largest, which agrees with the TEM measurements, and it also confirms the TEM insights as being the dominant lattice spacing. The 220 and the 311 peaks were comparatively weaker, but all three lined up with the expected diffraction peaks for the cubic or beta polymorph of silicon carbide. The y-axis is the intensity of the signal derived from the counts of the X-ray detector, and in these plots, the x-axis is just the Bragg angle measured in degrees. Optical absorption of the powder was performed by placing a small amount of carbon-removed powder in an isopropyl alcohol solution. The carbon had to be removed first so that the amorphous carbon coating would not interfere with the absorption signal, and an approximate band gap value could be determined through what is commonly referred to as the Talc Plot. The Talc Plot shows the photon energy on the x-axis here, and the quantity AHV to the 0.5 power on the y-axis, where A is the absorption coefficient and HV represents the photon energy that was absorbed. The exponent denotes the nature of the band gap transition, and a factor of 0.5 denotes an indirect allowed transition. The left figure represents the UV visible absorption plot of the silicon carbide nanocrystals, and the right figure represents the associated Talc plot, which, when extrapolated to the x-axis, shows a band gap of just under 2.4 electron volts for these nanocrystals. This agrees well with the generally accepted bulk band gap of beta silicon carbide, which is 2.36 electron volts. Also, we're currently measuring some smaller particles, which we now see exhibit some quantum confinement properties as well. In this study, beta polymorph small silicon carbide nanocrystals were made in a low pressure non-thermal plasma reactor. Silicon carbide nanocrystals of this size have never been made with this method before. The radii of the nanocrystal spheres were varied by changing the reactor pressure and the precursor flow rates through the reactor, and the sizes were confirmed by both XRD and TEM measurements. The TMS precursor had excess carbon that was consumed by hydrogen in the plasma, which engendered a stoichiometrically balanced end result. If the exact amount of hydrogen was not added to the unbalanced precursor, the powder ended up either carbon or silicon-rich, which formed an amorphous shell around the particles. The carbon-rich nanocrystals were soluble in short-chain alcohols, and the silicon-rich nanocrystals were not. The optical band gap of the nanocrystals was measured to be 2.4 electron volts, which was the same as the bulk polymorph. Future work could include more precursors. Phenylsilane groups, diethylsilane and hexylsilane are all potential candidates as a dual molecule precursor for silicon carbide. Each of those molecules that I mentioned has unique dissociation characteristics, which would change how and where it vaporizes in the plasma. Also, dual precursors with direct silicon and carbon molecules would allow for further tuning the silicon carbide ratio, which was shown in that ternary plot. You could get off that TMS and hydrogen constraint line. And more efficient use of the precursors could be allowed through increased yield because the carbon would not need to be consumed by the hydrogen gas, which would reduce loss. In the future, further functionalization and ligation studies could be pursued. If a clean surface of silicon carbide or silicon-rich material is present, the hydrogen passivated silicon atoms could undergo hydrosilylation, which is where an alkene or alkyne bonds with the surface silicon atoms on the double or triple bond site. And this would give it more solution properties similar to silicon nanocrystals, which have been studied extensively. That was what my presentation last semester was about, and there's lots of research done on silicon nanocrystals. Likewise, the carbon-rich shell surrounding the particles could be functionalized to make them react differently to their environment. Additionally, photoluminescence could be another avenue to explore. Devices using the nanocrystals could show future potential due to silicon carbide's distinct inertness and stability, especially when compared to unstable perovskites or even silicon. The powder collected from the reactor could also be experimented on further. Since the powder is so porous, sintering it and filling the matrix with other materials, such as polymers or other semiconducting materials, could yield physically robust, functional nanomaterial composites. In summary, silicon carbide is an inert substance which requires high synthesis temperatures. We made small silicon carbide nanocrystals without heating bulk amounts of material by utilizing energetic surface reactions in a non-thermal plasma. We collected crystals with sizes between 1.5 and 4.5 nanometers with both silicon-rich and carbon-rich shells. The amorphous carbon shells were removed by thermal oxidation, which increased particle solubility in alcohols. Big thanks to my advisor, Professor Hobby, for his guidance on the project and numerous insights. Also to the Hobby Research Group, notably Salim, who has helped out greatly with the characterization. And also Dr. Chad Pringle, who originally laid out many of the procedures and infrastructure before I started in on silicon carbide. Also Kenny Anderson, who assisted me in general chemistry advice throughout my master's. Also thanks to the committee members, Professors Troy and Rasmussen, their contributions. And additional thanks to R1A and R2 facilities and staff, without which much of the characterization wouldn't have been possible, like the XRD and absorption measurements. And also, thanks go to the funding sources. Thanks again, everyone, for attending today to learn about my research. Anybody have any questions?
Nice job, Reed. Just fire away if you have questions, please.
I guess I could go first. You mentioned that these nanocrystals can form in hexagonal orientations, and that makes me think of snowflakes, which form hexagonally. Can you build, say, these to get bigger and flat like a snowflake, or maybe longer and pencil shaped? Is there a way you can do that with your setup?
That's a good question.
That'd be nice. Yeah, we can make plates and tubes. That would be really nice. I'm not aware of anyone who's done that in a plasma, though. You need directional reactivity, and I don't see how you're going to get that in a. Only place that could come from is the flow. That's my take, Reed. What do you think?
Yeah, I think the same way. I mean, we've actually seen some lattices which are hollow. Like there's a paper that came out recently where they made like hollow silicon carbide nanocrystals, which is interesting. But yeah, nothing like asymmetric in one direction. So
thanks. Good talk, Reed.
Thanks.
Reed, you said that you can see what is it, cubic structure for larger crystals and hexagonal structure, I think, for very small ones. Do you actually observe this experimentally using X-ray or electron microscopy, or is this just a statement you made without seeing it actually?
Yeah, that's a good question. In our research, we always saw the cubic form, which was the beta form of the silicon carbide. And that was basically a statement that I made because that's what's been reported in other research. And that lined up with what we saw. We actually never saw hexagonal silicon carbide nanocrystals in our research. And we hypothesized that that's because it was so small. For some reason, the small nanocrystals are preferentially the cubic form of silicon carbide. So,
okay, thanks.
Yeah.
Thanks for the nice talk, Reed. So silicon's famous for having an indirect band gap. Is it known whether silicon carbide is indirect?
Mm-hmm. Yeah, it's indirect as well.
It is?
Yeah, it has similar band gap characteristics to silicon, except the band gap is much wider, giving it blue emission or green emission, depending on which polymorph. Like you can actually see if you, with the two different polymorphs, like if you have beta silicon carbide, the bulk band gap is about 2.36 electron volts. Whereas if you look at the hexagonal polymorph, the band gap is much larger, like 3.2 electron volts. So it depends on the polymorph, but they're all indirect from what I've seen, and they're all larger than silicon. So,
Which makes it hard to make them photoluminesce, I assume.
harder.
That's part of the problem anyway.
Go ahead, Reed. Tell them.
Yeah, it's harder. That and the surface chemistry is one of the hardest because there's an uneven amount of silicon and carbon in the powder. The surface chemistry is really hard to get to be pristine, which makes the best emitters. So that's another one of the reasons.
We have seen PL though. Salim's working on that. That's going to be Salim's project. So if you make these guys with an amorphous silicon shell, you can hydrosilylate. And then we see we're getting like 10% almost quantum yield. And it's the emission is in the blue and the green. Looks almost white. So Salim's going to do DGU on that soon. So yeah, it'll be really interesting. And lifetime, all that stuff. So yeah, we don't know. I think if you look in the literature on PL from silicon carbide, it's very confused. And I think that we may be positioned to actually answer this question for the first time here very shortly. So kind of exciting.
Nice. Good job getting that off the ground, Reed.
Thanks.
More questions? Had some good ones, because then if there's no more public questions, I think we'll just go to the committee. Any more?
I've actually got one.
Hey,
Yeah, first off, Reed, very nice talk overall. Yeah, really interesting overall too. I actually did have a question on slide number 20, I believe. It's the one with like the TGA plot.
Sure. Yeah, I'll pull it up. Share screen. Yeah, this one?
Yeah, that's the one. Something I noticed on there too. Yeah, I noticed that you talked a lot about the mass sort of decreasing as time goes on. Something I noticed is that like around the time of like, was that 25 to like 75 or something, 25 to 75 minutes, there's like that sharp increase in the mass as well. So I'm just kind of curious on what's actually like causing that overall.
Sure, yeah, that's an astute observation. Basically what's causing that, to the best of our knowledge, is that there's a certain amount of basically precursor that reacted in the reactor, like these carbon groups, and they don't all form versions of carbon that just go straight into the vacuum pump. Some of them are longer chain carbons. And a lot of those will take on oxygen groups. So as you oxidize it or as you heat it up, they'll actually, the way that those ones will oxidize, well, they'll actually take on oxygens. And then eventually, when you reach this peak energy or this peak temperature, then they'll start to burn off that oxygen again as they evaporate. So that's what we've seen. And the final powders do give us like those absorption measurements kind of confirm that as well. We're getting absorptions that make sense for pretty pure silicon carbide. So
Interesting. Yeah. All right. Yeah. Thanks for explaining that as well.
sure. Did that make sense?
Yeah, that makes sense. Yeah.
Cool. Good question.
Okay, any more questions from the public? Thanks, everybody, for coming. We appreciate your interest.